Hi everyone, today we're going to talk about water potential. Water potential is going to predict the direction of water movement. So we're going to be looking at which way water is going to move in different scenarios. It describes the tendency of water to leave one place in favor of another, and water is always going to move from an area of higher water potential to an area of lower water potential. There are two different things that are going to affect water potential. One of them is the pressure and the other is solute. So when we think about water potential, there's two things that are going into it, pressure potential and solute potential. And to get our final water potential, we just add them up together. So when we're looking at water potential, if your container is open, like this beaker, there's no lid on it, that's going to have zero pressure potential. And since we're looking at distilled water, there's no solute, that means there's going to be zero solute potential. So 0 plus 0 equals 0. Great work. As we add solute, we're actually going to end up lowering the water potential. So here you can see we've got distilled water, which we already talked about has a water potential of 0. If we take this plant cell and we drop it into this beaker of distilled water, we're going to notice that water's moving in, and that makes sense. But if we explore the math behind it, we can realize that the pressure potential of the plant cell is 0, but the solute potential is a -2. And our total water potential then is -2. Since the water is always going to move from high to low, 0 is higher than -2, so water is going to move from the beaker into the cell, which is exactly what we expected. Now, as the water moves into the cell, we're going to start to get this turgor pressure against the inner cell wall, and that is going to raise our pressure potential to a +2. We have a +2 pressure potential, a -2 solute potential, and that gives us a grand total of 0. So if our beaker of distilled water has a water potential of 0, and our plant cell also has a water potential of 0, water is going to move back and forth at the same rate. And that's what we call dynamic equilibrium. So let's look at this little math problem here in this corner. The beaker of water has a solute potential of -12 and a pressure potential of 0 because it's open, and so that gives us a total water potential of -12. If this plant cell and this solution are in dynamic equilibrium, they must have the same water potential. So we're going to write down a -12 here for our water potential. It tells us that the solute potential is -15, which means this pressure potential must be a +3. We've got a couple of practice problems on the back. Number 1, if a plant cell's pressure potential is 2 bars and its solute potential is -3.5 bars, what is the resulting water potential? So we know that We know that water potential is our solute potential plus our pressure potential. Our pressure potential is 2 bars, and our solute potential is -3.5. That gives us a grand total of -1.5 bars for our water potential of this plant cell. Number 2, the plant cell from question number 1 is placed in a beaker of sugar water with a solute potential of -4 bars. In which direction will the net flow of water be? So let's label really quickly that this is our plant cell with the -1.5 bars, and our sugar water has a solute potential of -4 bars. Since it's in an open beaker, we can say that the pressure potential is 0, plus our -4 bars of solute potential. That gives us a grand total of -4 bars. To figure out which way the water is going to flow, we're going to look for the water to go from high to low. -1.5 is higher than -4, and so it's going to go out of the plant. We have one more fancy new formula to learn. Our solute potential is going to equal negative I CRT. So our negative I is just our ionization constant. For sucrose, it's 1 because sucrose isn't going to fall apart in water, but salt will fall into its 2 pieces. So for salt, our ionization constant is 2. C is just our molar concentration. R is our pressure constant, which is always going to be 0.0831. And then our temperature is going to be in Kelvin. And to convert from Celsius to Kelvin, we're just going to add 273. So let's do one more practice problem together. The value for water potential in root tissue was found to be negative 3.3 bars. If you place the root tissue in a 0.1 molar solution of sucrose at 20 degrees Celsius in an open beaker, what is the water potential of the solution, and in which direction will the net flow of water be? So I like to break it up, and I like to talk about just the root first, and then we'll talk about the beaker. The water potential in the root is negative 3.3 bars. We don't have to calculate anything there. For the beaker, we know that our water potential is going to be our solute potential plus our pressure potential. Our solute potential is going to be negative ICRT. So since we're looking at sucrose, our ionization constant is 1. This is a 0.1 molar solution. Our pressure constant is 0.0831, and our temperature is 20 degrees Celsius, so we're going to add 273 to convert that to Kelvin. Once you multiply all of that out, let's see what you get. You should have gotten negative 2.43 bars. That's our solute potential, and we know that our pressure potential was 0 because it's an open beaker. So our water potential is negative 2.43 bars. Remember that water potential is always going to go from high to low. In this case, negative 2.43 is higher, so it's going to go from the beaker into the root.